Welcome. In this video, we are going to implement the Siren paper developed at Stanford. So what this paper is trying to do is to represent function as implicit neural representations. So that means representing signals such as 3D models or images with neural networks. So for example, if we focus on images for now, let's have a look at this image on the leftmost side. So usually in a computer vision, they are represented as 2D grids of pixel values. Which of course is then you have a discrete signal and you are limited by the resolution of your representation. And as neural networks are omnipresent now, what you can be tempted of doing is to represent this image with a neural network instead. So you will take as input a position. So for example, the XY coordinate in the image, and at that position you will output the value at that position. And therefore you can now have a continuous representation of your signal because neural networks are continuous. That's super simple to do because you just have two inputs, the coordinates, XY coordinates, and you output only one or three values, the pixel values. One if it's a black and white image, three if it's a color image, the RGB channels. So very simple task, but if you try to do that, so to overfit a neural network on that image to represent it, you will get those results that are really blurry. If you do that with a standard neural network with ReLU activation functions. So although the task is very simple, the results are very bad. And this is because neural networks are biased to learn low frequency signals. And images are high frequency signals, and therefore you get this image that is very blurry and that is very that has low frequencies. And therefore, if you want to get a great result, such as the one on the right, obtained from the Siren paper, you need to bias your neural network to learn high frequency signals. So you need to put inductive bias in your neural network so that it will learn high frequency signals. So there are papers like NERV that do that by using positional encoding, but the Siren paper suggests this idea that seems very simple. It's just to use sign functions as activation functions rather than the ReLU. There are also other things you need to take care of, such as you need to be careful about the initialization of your neural network. But apart from that, the idea is very simple. And if you compare the PSNR between the trained models and the controlled image, you can see that the Siren is doing a very good job as opposed to the ReLU activation functions. So let's dive directly in the implementation. So we'll use PyTorch to do that, and we'll use some other libraries, some helpers such as NumPy and Matplotlib for plotting the results. So we will need to create our activation functions. And this will be very simple. It's just a sinus functions with some frequency W0. So very simple. This will be what we'll use instead of the ReLU. Then we can create our neural network. We will call that Siren. And as you can see, it's just a simple MLP. But instead of using ReLU functions, we use sinus layers that we've just created. So by default, we will use a frequency of 30. We take, as we've said, two input dimensions, the coordinates x, y. Let's use a hidden dimension of 256. As you are treating black and white images, we only need to put one output dimension that will be the intensity of the image at that coordinate. That's almost done. What we need to do is to be careful about how we initialize the neural network. If we just define the neural network like this, it will be, I think, initialized with Xavier initialization, which is what PyTorch does by default. But if you use sign functions, you need to be careful about how you initialize the neural network. And there are a specific distribution you should use that are described in the papers. So basically, you need to initialize your the weights of your linear layers with those functions. We can have a look at that in the paper. I won't go through that in detail, but this is discussed there. And basically, this is what you want to use in your initializations. And this is very critical. If you don't do that, you won't have good results. So far, so good. So once you have created your neural network, you've initialized it. We've override the forward function from PyTorch, and therefore when we get an input coordinates x, we just forward it to the neural network. So we want to compare Siren to MLP. So let's just create a simple MLP. So standard MLP with the same hidden dimension, the same number of layers, but we use the ReLU activation function instead. And then we can create a function for training our models. So the training function, basically we're just doing a regression task, so very easy. We take a model as input, an optimizer. We train for a given number of epochs, 15,000 by default. And then what we do, we get the input, so the pixel coordinates. We get the output at those coordinates. Then we take the MSE loss between the target and the output of the model. We log the PSNR, and then we do the gradient update. And then we're ready to do the training and to use our functions. So we create a Siren model, we create an MLP model. Then we load our data. So we will use the camera image that is well known, and we can retrieve it very easily by using SkyImage that we have imported previously. So we load the image, we normalize the data so that the pixel values are between -1 and 1. It's always better when we train neural networks, and then we reshape them in 1 dimension rather than 2. So basically these are our target values. This is what we want to predict. So we have our target values. Now we need to create the inputs. So we will create a 2D grid of values that go between -1 and 1. If we go back to the results, so here we have the corner -1, -1. Here the corner -1, 1. 1, -1, and 1, 1. And therefore we can give any value that is between -1, -1 and 1, 1. And we will be at 1 point in the image, and we can predict the value at that position. So once this is done, we can start training our neural networks. So I'm already creating a figure. So I'm plotting the ground truth image on this plot where I have 5 subplots. So first I will plot the ground truth image, then I will plot my trained models, and then I will plot the training curve or the PSNR. So then we can iterate over the 2 models, so the MLP and the Siren model. For each model, we will train it using the training loop we've created. We will train them using the Adam optimizer. And then we can plot the results. So we, for the predicted pixel values, we plot them. And yeah, we do a lot of extra steps for just setting the title, the labels, and so on and so forth. And then we do an extra loop just to remove the text. We remove the axes, and then we save the figure. So very easy, simple paper, but yeah, there is quite some maths behind that. The most important part is this initialization, and you can see that just by adding these functions instead of ReLU, and by using this careful initialization, you get much better results. So these are the results you will get after training the neural network. I don't think you need to, if you don't have a GPU, I think it should run fast on CPU. So thank you for having followed this video to the end. I really hope it was helpful to you. Please leave the thumbs up if it was, to help this channel get known, and subscribe for more videos like that.